So let us consider the first chapter here, that is single phase transformer. So the syllabus contains review of EMF equation and equivalent circuit. Why this is a review topic? Because you have learned single phase transformer in your basic electrical theory course. Okay, that is why we will have a review of this topic, that is EMF equation and equivalent circuit. Next we have phasor diagrams on no load and full load. This also you have learned in basic electrical theory course. Then per unit representation of transformer parameters, this is a new topic. Voltage regulation, this also was there. Losses and efficiency also was there. OC test and SC test was there. All day efficiency, this is a new topic. Okay, so this single phase transformer, most of the topics you have already covered in basic electrical theory course. Okay, and parallel operation of transformers, this is also a new topic. So let us start with some introductory concepts. So this diagram shows different sizes of transformers. That means it is from the application point of view that transformers are a very important part of electrical and electronic circuits, and its sizes from and it sizes are so varying. That means it weighs, in case of electronic circuit it weighs about a few grams, and in case of power system it may weigh about hundreds of tons. Okay, so and you will find the application of transformer in every electronic circuit, and the distribution of power, electrical power, depends on the transformer. Okay, you can see this is a power supply system scheme. Here it starts from the generating station where the voltage is generated at a level of 11 or 11.5 or 12 kV. Okay, and this voltage is sometimes stepped up or stepped down as per requirement at different stages, and at the consumer end it supplies at a voltage level of 400 or 230 volt only. Now why this step up and step down is required, that is already described in your basic electrical theory paper. That means to minimize the distribution and transmission losses. If the electrical power is transmitted through at a very high voltage level, then the loss which occurs in the conductors, that will be reduced. That is why this at different stages this voltage level required to be reduced or increased as per our requirement. Okay, so this voltage level increment or decrement, that is done by this transformer. That is why transformer is so important in case of electrical power systems network or electronic circuit. Okay, so this is a picture showing a three-phase transformer. Normally three-phase transformers are used as a three-phase bank. Three-phase bank means three single-phase identical single-phase transformers are connected to work as a single unit, as a single three-phase transformer. Okay, normally three-phase transformer as a single unit, it is not built. We use three identical single-phase transformers to act as a three-phase transformer, and this is a smaller one. Which this type of transformers are normally used in electronic circuit. So let us define what is a transformer. The transformer is a device that transfers electrical energy from one electrical circuit to another to another electrical circuit through the medium of magnetic field and without a change in the frequency. So here we are transferring electrical energy from one circuit to another circuit. Then the question arises, why do we require this transformer? Because we are transferring electrical energy from one circuit to another circuit. Okay, so why this transformer is required? Because in between this two circuits we require uh, a voltage level change or a current level change. Okay, so that is done by this transformer. That means when transformer is supplied by some voltage source, AC voltage source, at a certain voltage level, at the output, that means at the other end, other circuit, we are getting a voltage level which is different from the supply voltage. Okay, so to change the voltage level we require a transformer. So here transformer is a device which transfers electrical energy from one circuit to another circuit by some magnetic coupling. Okay, so first of all, the energy supplied to this transformer that is that is first it is getting transferred into magnetic energy, and that magnetic energy is reconverted into electrical energy in the second side, I mean secondary side. Okay, so the transformer transfers electrical energy from one circuit to other circuit. That means this first side where the electrical supply is connected, that is called the primary winding. In transformer there are two windings. One winding is connected to the supply system, because the transformer transfers electrical energy from one circuit to another circuit, then it has to be connected with some source of energy, because this transformer cannot produce energy by itself. Okay, so it has to be connected to some source of energy. So that source of energy is connected to one of the winding. So the winding to which the supply system is connected, that is called the primary winding, and the other winding which is connected to the other electrical circuit, that is called the secondary winding. Is it clear up to this?
Yes, sir.
Yes. Okay. So now this transformer is an electromagnetic energy conversion device. Why is it so? Because first of all, we are giving some electrical energy to its primary winding, and that energy is first converted into magnetic energy, and then it is reconverted into electrical energy in the other winding, which is supplied to the second circuit. Okay, that means the circuit which is connected to the secondary winding. So there are two steps of energy conversion. First of all, electrical energy is supplied to the primary, which is converted into magnetic energy in the magnetic coupling, and then this magnetic energy is reconverted into electrical energy in the secondary winding. Okay, these two windings, the primary winding and secondary winding, they are not electrically connected, they are magnetically coupled. And to do this magnetic coupling, we need one ferromagnetic core. Okay, and this magnetic field allows the transfer of energy in either direction. That means we are uh, calling this the two windings of this transformer as primary winding and secondary winding. These are not fixed. Suppose we are considering this transformer which is an isolated transformer, that means it is not connected to any electrical circuit, neither to a source nor to any electrical load. Okay, in that case it is in that case we are not able to identify which one is the primary winding and which one is the secondary winding. Okay. Let us consider this schematic diagram of a transformer. Here this is the ferromagnetic core. This section, this whole section is the ferromagnetic core. In first leg, that means this one, here one winding is there having n1 number of turns, and this is called the primary winding for this case, because the supply system V1 is connected to this winding. And this is the secondary winding, which is receiving the energy after it is transferred from primary to secondary through this magnetic coupling. Okay. Here the secondary winding is not connected to any circuit or any load, it is open circuited. So secondary winding is having n2 number of turns. Now there are three possibilities. One is n2 is greater than n1. In that case, this voltage induced in the primary, suppose E1 is the voltage induced across the primary, and voltage induced in the secondary is suppose E2. So in that case, E2 will be greater than E1. That means we are giving voltage level across the primary, and we are getting a higher voltage level across the secondary. So this kind of operation is called a step up operation, and we can call this transformer as a step up transformer. The second possibility is N2 is less than N1. In that case, this E2 will be less than E1. So that will be a step down operation, and for that case we can call the transformer as a step down transformer. Okay. Another possibility is there, that is N2 is equals to N1. In that case E2 will be equal to E1. So there will be no change in voltage level. So this is another application of this transformer, where we require to isolate two electrical circuits electrically. That means there will be no electrical connection, but it has to be supplied by some voltage source. Okay. So in that case we can use this kind of transformer, which is known as isolation transformer. Sorry. Okay. So here E2 will be equal to E1. So this is called isolation transformer. Okay. So step down and step up transformer, these two terms actually does not have any meaning, because step up transformer can also be used as a step down transformer. How? If we change the connection, that means step means we are giving supply to the winding which is having lesser number of turns, and we are taking output from the winding which is having larger number of turns. That means the secondary side N2 is greater than N1. Now if we change the connection, that means now we are giving supply to the turns, winding having N2 number of turns, which is greater. So this is our primary now, and in that case the output will be less than the input voltage, so we are getting a step down operation. So in that case uh, we are performing the step down operation using the same transformer. So that is why there is no transformer as step down transformer or step up transformer. Only we can call the operation as step up operation or step down operation. Okay. So transformer can only be termed as step up or step down transformer only after it has been put into operation. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
So there is no step up or step down transformer. There is only step up or step down operation. Okay. So how to identify the windings in that case? We have to mark the windings. So in that case, we can mark the windings as high voltage winding and low voltage winding. High voltage winding means the winding which is having larger number of turns, and low voltage winding means having lesser number of turns. That is fixed. Whatever may be the operation, these high voltage winding and low voltage winding remains fixed. If you connect supply to the high voltage winding and take output from the low voltage winding, that will be a step down operation. If you connect supply to the low voltage winding and taking output from the high voltage winding, that will be a step up operation, isn't it?
Yes, sir.
So is it clear, this step up and step down operation?
Yes, sir.
Okay. So that is all about this introductory concept. Now we will review this construction of transformer, because that is necessary to understand the basic principle. So there are mainly two types of transformers depending on the construction of core. So one is core type transformer, another is shell type. So this is a core type and this is a shell type. Observe the difference. In core type there are three limbs or legs. These vertical sections are called limbs or legs, and the horizontal sections are called yoke. Okay. So how this core is made of? The core is a stack of thin steel laminations about 0.35 millimeter thick for 50 Hz transformers. Okay. So this 0.35 millimeter thick laminations are stacked one over other, and in between any two stacks there will be some insulation, so that the these laminations are placed to decrease the eddy current losses. Okay, so how this eddy current losses will be decreased if you put some insulation, that I will discuss later on. So first of all, consider the construction here. So the core is made up of thin steel laminations, and these laminations are stacked one over the other to form this kind of core. Okay, so here how these two types are uh, different from each other. These are different from the how the windings are placed on the limbs or legs. In case of core type, you can see two legs are used to place the windings, but in case of shell type, only one leg is used to place the windings. Okay. The core material is used as this CRGO steel. What is this CRGO steel? This is a special type of steel which is known as the cold rolled grain oriented steel, and this steel reduces the magnetic loss, that is core loss. Okay, there are two types of core losses. One is eddy current loss, another is hysteresis loss. Eddy current loss can be minimized using this stack of laminations, and this better magnetic materials is used to reduce the other loss, that is hysteresis loss. Okay. In case of shell type construction, you can see the most part of the windings are covered by the core, but in case of core type, you can see the most part of the core is covered by the windings. That is the basic difference. And we can go back to the schematic diagram. This was the schematic diagram. You can see here the whole primary winding is placed on one leg, and on the other leg the whole secondary winding is placed. So this is not the actual connection, actual physical orientation of the windings. To reduce the leakage flux, this leakage flux I will discuss in detail later on. So to reduce this leakage flux, these windings are placed in this way. You can see from this diagram. First of all, half of the low voltage winding is placed on first leg, this section. Then the other half is placed on the other leg, this section. First of all, some insulation is there. This section is for some insulation in between core and low voltage winding. Then another insulation section is placed. Over that insulation, this half of the high voltage winding is placed here, and in the second half, similarly, other half is placed over the insulation. That means first of all some insulation, then half of the low voltage winding, then some another layer of insulation, then the other half of the high voltage winding. In this way, these windings are placed on the two legs. Okay, so this is for core type. But in case of shell type, this type of windings are called sandwiched or interleaved winding, because you can see first of all half section of low voltage winding is placed, then over that half section some full section of high voltage winding is placed, then another full section of low voltage, then another half section full section of high voltage winding, then half section of low voltage winding. In this way, one after another sections of low voltage winding, that means one by first of all some insulation to insulate the winding from core here, then low voltage winding, then another layer of insulation, then high voltage, a full section high voltage. That means the top section and the upper section of low voltage winding are two half sections. This type of windings are called interleaved or sandwiched winding. Okay, so these are the main differences between these two types of construction. So all these are needed to minimize the leakage flux. So this leakage flux is very important, and that I will discuss in detail in later part. So for the timing, this much of construction is sufficient for you. So is there any question?
Sir, which type of transformer is better?
That depends on application. No one is better than other, and also it depends on cost also. What type of application you are designing for, and who is buying it. The buyer is able to pay much or less. That is also another condition while designing. You can see while this transformer will be in operation, there will be a huge amount of losses, both core losses as well as copper losses. So due to those losses, there will be heating effect. So for cooling or to radiate those heat, you need sufficient cooling arrangement. So if the losses are very high, then in that case this cooling for port type of transformer is better. You can see, I mean, natural cooling. And for shell type of transformer, you will be requiring forced cooling. There are different types of cooling methods. You can you might have seen in larger transformers there are some blade shaped arrangements, and beside that blade shaped arrangement some fan is revolving. Okay, so those are forced cooling. So if you can arrange those type of arrangements, then this shell type of transformer can be used, because here the windings are covered by this core, so you need extra cooling arrangement. But in case of core type, if the transformer rating is very high, then in that case you also will be requiring this extra cooling arrangement. But for smaller transformer, you don't require any extra cooling arrangement. Natural cooling will be sufficient. Okay, so there are so many constraints. Is it clear?
Yes, sir.
Okay, so next we are having this topic, that is review of EMF equation and equivalent circuit. First of all, let us consider the EMF equation. So basic principle of transformer and EMF equation. So a transformer works on the principle of electromagnetic induction, that is mutual coupling between two or more coils. So tell me, what is this electromagnetic induction? Anyone?
Change in magnetic flux generates electricity.
Repeat. Hello? Repeat, please.
Change in magnetic flux generates electricity.
Change in magnetic flux? Your voice is
Induces
breaking.
EMF.
Yes.
The change in
If there is,
magnetic flux induces EMF.
yes, if there is any change in magnetic flux linking with some winding, then there will be some induced EMF in that winding or coil. Okay, so that is the basic principle of electromagnetic induction. Now this change in magnetic flux linking with some coil, we can call it flux cutting action, or change in magnetic flux. Flux linkage, not flux linkage. Flux linkage is equal to flux into number of turns in the coil. Okay, so if there is any flux cutting action between this flux and some coil or conductor, or we can say if there is any change in flux linkage, then there will be some induced EMF in the coil or conductor. Okay, now for this flux cutting action, we require either a constant magnetic source with movable conductor, or I mean the relative motion between the source of magnetic flux and the conductor. The source of magnetic flux or the conductor either may move. We only require relative motion between these two, or we can have static magnetic source as well as static conductor, but the magnetic flux itself will be time varying. Okay, so first one, where the relative motion is required with a constant magnetic flux, in that case we call it a rotational EMF or motional EMF. And the second case where the flux itself is a time varying quantity, in that case we call it a transformer EMF. Okay, so here in this case we are going to consider the transformer EMF. Why? Because transformer is a static device, there is no motion, both the windings are fixed. So one of the winding will produce the magnetic flux which will be time varying, and to produce time varying flux we require time varying current. Okay, and time varying current will be produced by time varying voltage source, that is obvious. So the transformer works only for uh, for AC type of voltage source. Okay, the transformer does not work with DC voltage source. If you connect some DC voltage source to one of its winding, then across the secondary you will not get any voltage. Okay, so here we are going to derive the transformer EMF. So what happens when these two coils are placed close to each other and one of the coil is supplied from a AC voltage source? In a single word, we can say that electrical energy is transferred from the winding which is connected with this supply to the other winding by electromagnetic induction. But how this energy transfer is occurred, that we have to understand. So first of all, when this, consider this schematic diagram here. In leg 1, this primary winding having N1 number of turns are wounded, and in the secondary, that is P is the primary winding, S is the secondary winding having N2 number of turns, and primary number of turns are N1. So primary winding is connected to the source V1. V1 is an AC voltage source. Okay, so when this AC voltage source is connected to the primary winding, there will be a closed path, so some current will start to flow through this N1 number of turns. So when this alternating current flows through this N1 number of turns, what happens? It will produce its own MMF, that is magnetomotive force, which is equal to the current. Suppose this current is I, E, and N1 is the number of turns in the winding. So IE N1, that is the MMF produced by this primary winding when it is supplied by this voltage source V1. Okay, now this MMF will produce its own flux. So what is the formula to calculate flux? Flux is equal to MMF per reluctance. Okay, so MMF IE by N1, if you divide it by the reluctance, you will get flux. So this primary winding will establish or produce a flux which will remain confined within this ferromagnetic core. This is our ferromagnetic core. So the flux produced by this primary winding will remain within this ferromagnetic core. Okay, that means whatever flux is produced by this N1 number of turns, all the flux will remain confined within this ferromagnetic core. We are assuming that there is no leakage flux. Again, the term leakage flux is here. So what is this leakage flux? Leakage flux is that flux which is produced by one winding and linking with the same winding, and it is not linking with the other winding. Suppose this primary winding is producing this flux phi and some leakage flux whose path will be like this. Okay, obviously it is linking with the primary winding only, and it is not linking with the secondary winding. but the flux phi, it is linking with both the windings. So that is, this phi is called mutual flux, and this flux is called leakage flux. I will discuss this leakage flux in more details also again. So first of all, we are giving supply to the primary winding, and it is producing its own flux phi, and that flux remains confined within the ferromagnetic core. And since the secondary winding is also placed on the same core, so it is linking with the same flux. Then what happens? This alternating flux, which is linking with both the windings, it is producing EMF, inducing EMF E1 across the primary winding and EMF E2 across the secondary winding. As I have already mentioned, the flux is alternating in nature. It is time varying. So whenever there is a flux cutting action, that means change in flux linkage, there will be some induced EMF. So this, when this time varying flux is linking with this primary winding as well as this secondary winding, so there will be two induced EMFs, one E1 across the primary winding, another E2 across the secondary winding. Okay. Now if some load is connected across the secondary winding, suppose this is our load, then some secondary current will also flow through this secondary coil, but that is not required now. Let us consider the current produced by this alternating voltage source. So let us consider the current expression as Im equals to I max sin omega t. Now you can see in the diagram we are showing the current as IE, but we are writing the expression as Im. Why these two currents are different? Actually, when there is no load across the secondary side, to establish the flux we require a current which is Im only. This current is called the magnetizing current. This Im is responsible for the production of flux only, but when this flux is produced, there will be some losses in the core, inside this core, both eddy current loss plus hysteresis loss. So we require a more a little bit of more current. That means this winding will extract more current from the source. So another component of current is there, which is called core loss component. Now for the time being, and these two currents is equal to IE, that is called the exciting current. So this current is exciting current, and this current is core loss component of exciting current, core loss component. Now for the time being, we are considering that this transformer has no core losses. Okay, that is why this IE and IM are same. This component is absent now. So that is why in the diagram we are showing this current as IE, but we are writing the expression as IM. IM is magnetizing current which is producing this flux, and IE is exciting current whose one of the component is IM. For the time being, we are considering the core loss, other component of IE, that is core loss component, is equal to 0. That is why IM and IE are same. Is it clear?
Yes, sir.
Yes, sir.
So when there is no load connected across the secondary, the transformer primary current is only the exciting current IE, and IE is the phasor sum of IC and IM. IC is core loss component, IM is magnetizing component. Core loss component is responsible for the core losses inside the core. IM is responsible for the production of magnetic flux. Okay. So for the time being, we are considering that this transformer has no core losses, therefore IC equals to 0, therefore IE equals to IM, that is the magnetizing current only. Okay. So Im equals to I max sin omega t. Normally we express any current as I equals to Im sin omega t, where Im is the maximum current or the maximum amplitude, but this current itself is denoted by the symbol Im. That is why this is I max. Okay. And omega t, t is the variation, t denotes the variation with respect to time, and W is the angular frequency in radian per second, that is the supply frequency, and W is equal to 2 pi f, where f is the frequency in hertz or CPS, cycles per second. So when this V1 is connected across the primary winding having an N1 number of turns, the current I starts to flow through this N1 number of turns. Okay. Or we can say the current Im starts to flow through the N1 number of turns, because IE and Im are same. So therefore the MMF produced is equal to N1 Im, or you can write N1 IE also. Now if we consider S as the reluctance of the core, then flux produced by the primary winding is given by phi equals to N1 Im by S. Now if we put the value of Im in this equation, then we will be seeing that since Im is sinusoidal in nature, because the expression of Im was Im equals to I max sin omega t, so we can say this flux is also sinusoidal in nature. So we can write phi equals to phi m sin omega t. Since Im is sinusoidal in nature, therefore phi is also sinusoidal in nature. Okay. So now we have the expression of flux, time varying flux, phi equals to phi m sin omega t. Now what is the principle of electromagnetic induction? That is Faraday's law of electromagnetic induction. We know the mathematical expression E equals to minus of n d phi dt. So putting using that equation, we can write E equals to E1 equals to minus of n1 d phi dt. Here E1 is the induced EMF in the primary. Why this small letter is used? Because this is the instantaneous value. Okay. So putting the value of phi and taking derivative with respect to t, we get E1 equals to minus of n1 omega phi m cos omega t, or we can write E1 equals to n1 omega phi m sin omega t minus 90 degree. Please mute yourself. Someone's mic is not muted. So this is the instantaneous value or the expression of induced EMF in the primary winding. And from this expression we can find the maximum value, that is EM1 is equal to N1 omega phi m, that is equal to 2 pi f N1 phi m, and to find the RMS value we need to divide this maximum value by root 2, this you know. So RMS value equals to this, capital E1 is equal to root 2 pi f N1 phi m. If you put the value of pi, you will get E1 equals to 4.44 f N1 phi m. So that is the expression of primary induced EMF RMS value or RMS expression of primary induced EMF. Any question up to this?
No, sir.
Okay, then today up to this time is over.
Thank you, sir.
So can you share the PDF with us? Syllabus
Just a
PPT
minute,
allow-
just a minute, just a minute. Don't leave. I have to take attendance.
Yes, sir.